An introduction to sets in GAMS. In this video, we will give an introduction to static sets, dynamic sets, and multidimensional sets. Furthermore, we will write a GAMS program that aims to illustrate how sets can be used in a model. In some statements, the $control operator is used to control a set. If something is left unclear, then I hope that the GAMS User's Guide or Expanded Magal Guide can help you. We will introduce sets by looking at a simple model. We consider the problem where we want to minimize the cost of storing 30 items over a 1-month period. We have 3 storages at our disposal, and the storage availability changes weekly. Each storage has a storage cost per item. Furthermore, there is a shipping cost per item from one storage to another. We need to decide in which storage the 30 items should be stored each week. First, we introduce sets. We use the keyword set to declare a set. W is the set identifier or name, and week is the set description. The set elements can also be called members or labels, and they are defined by listing them between slashes and separating the elements with a comma. A set member can also have a description. The asterisk expands the set to include a sequence of set members. Hence, the domain of set S includes the elements S1, S2, and S3. Set W and S are static sets because the members cannot be changed. Next, we will consider dynamic sets. Dynamic set D1 can only include members of the domain set W. D1 is therefore a subset of domain set W. The dynamic set D2 and D3 are declared, but their members are not defined. It is good practice to define a set instead of assigning it if it is possible. I will soon explain the assignment of a set. Note that we can use the set D1 as domain for set D3. However, if we use set D2 as domain for set D3, then the domain for set D3 will be unknown. Sets D2 and D3 are declared without being defined. Next, we will assign sets. We will assign elements to sets D2 and D3. In the first statement, keyword yes assigns all the members of the domain set W to set D2. By referring to a specific set element and the keyword no, we can exclude a specific element. We can also use the OR and card operator to control the assignment. In this case, after the keyword yes, we use the $operator. The $operator evaluates the logical condition that follows the operator. OR returns the relative position of a member in a set. Card returns the number of elements in a set. The angle brackets between OR and card denotes not equal. Don't forget to surround the logical condition with parentheses. We can also leave out the keyword yes. Hence, all members in set W are assigned to set D3 except for the last set member. We can use the display statement to see that the assignment are done as we intended them to be. Multidimensional sets. Next, we declare the multidimensional set Avail. The set Avail denotes the storage availability. In the table, we can see which week a storage is available. A 2-dimensional set is mapped by defining set member pairs. To denote a set pair, we use a period between the connected set members. Pairs are separated with a comma. Parenthesis provides a list of elements that can be expanded when creating pairs. The asterisk sign can also be used to expand the sets. This is a compact way to map the 4 pairs. The number sign or hashtag character can be used to denote all the members of a domain set. We can check that the intended assignment has been done by using the display statement. Next, we will assign multidimensional sets. The alias statement gives a second name for the same set. Sometimes we need a second name for a set in order to specify the problem without ambiguity. Here we call the alias sets S' and W'. Set WSS is called a tree tuple, and it is declared with the domains sets week, storage. The set WSS maps for each week from which storage to which storage items can be shipped. Let's first map all alternatives except if the source and target storage are the same. Here we need to use the aliased set S' to unambiguously refer to the set elements. Storage pairs with different sequence numbers will be mapped. The mapping is done for all weeks because set W is not restricted in any way. We can use the command line statement gdx equal to temp in order to write a gdx file. Now we can inspect the resulting gdx file to see if the assignment is as we intended it to be. We can move the identifiers in the window to conveniently verify that there are no shipping possible between the same source and target storage. Next, we take in consideration when the source storage is available, and therefore include the restriction of Set Avail. We enforce both the logical conditions by connecting the conditions with the keyword AND. We also need to require that the target storage that we ship to is available. The assignment is done by combining three logical conditions. We can check this by using the display statement. We can see that at week 1 we can ship from storage 1 to storage 2 and 3. We can also see that we can ship from storage 2 to storage 3. Looking at storage availability table, this makes sense. Next, we will use projection. We can use projection to define the shipping alternatives without the domain W. We use the keyword option and specify first the set to perform the projection on, and after the less than sign, the source set. We can use the display statement to see the differences between set WSS and set SS. We can see that set SS has lost the information of week, but maps only shipping alternatives that can be found in set WSS. Next, we define the input data. First we define the number of items to store, then the capacity of the storages, and finally the storage cost of the three storages. Next, we define the shipping cost. The shipping cost is defined from one storage to another, hence shipping from storage 1 to storage 1 is not possible. We can assign the mirrored relations by using the dollar control. Note that we have sets S' and S on the left hand side and the opposite order on the right hand side. The dollar control condition restricts the assignments, in this case, to the storage connections that are not yet assigned. We can check by using the display statement that the intended assignments were done. Next, we will write the variables and constraints of the model. We declare the variables total cost, storage quantity, and shipping quantity. The first constraint sums up the total cost of storing and transporting items. The second constraint allocates the 30 items in week 1 to one of the 3 storages. The third constraint keeps track on where the items are. For the moment, we comment out constraint 2 and 3 and consider only constraint 1. The first constraint sums up all costs of storing and shipping items for the 3 storages over 4 weeks. We can first sum up all the costs of storing items by multiplying the storage cost per item with the number of items in the storage for all storages and all weeks. Next, we will check the correctness. However, before that, we need to complete the model. we declare the model and use options limRow and limCol equal to 100 in order to allow all constraints in this example to be listed in the equation listing. We also add the solve statement. We run the model and open the GDX file. We organize the entries by number of elements. We see that in Set Avail we have 9 set members, but we have introduced 12 storage variables. We can then open the listing file and look at section Equation Constraint E1. We can see that storage 1 at week 2 is present, even though it is not available for us to use. Clearly, if the variable storage 1 at week 2 is present, then it must be 0. Hence, it can also be removed from the model. Looking at the constraint E1, we can notice that we did not take the storage availability into consideration. We can use the dollar condition and restrict the summation indices to the available storages defined by Set Avail. Next, we will check the correctness. We can see that storage 1 at week 2 is not longer in constraint 1. However, a better way is to directly use the Set Avail, because now the logical condition does not need to be evaluated and the constraint requires less space. Note that we can use in the summand any set identifier that is used for the summation index. Hence, we can use the Set Avail as set index for storage variable. In addition, we need to add the shipping cost to the total cost. This follows the same logic as previously. Here we restrict the summation indices to the already defined shipping alternatives in the set WSS. Then we multiply the shipping cost with the number of shipped items. Next, we will check the correctness. We can see from the GDX file that both Avail and storage has both 9 elements. We can also see that both WSS and ship has both 7 elements. This is a good indication for our example because we have not introduced more variables than necessary. From the equation listing we can see the constraints in expanded form. It may be easier to verify the correctness of the constraints when they are in expanded form. Constraint 2 places the 30 items at week 1 into one of the 3 storages. We can check the correctness from the listing file. We can see that constraint 2 is how it is intended to be. Constraint 3 describes the storage level for weeks 2 to 4 for each storage. Therefore, we can use an indexed equation that produces a separate explicit constraint for each week and storage. The dollar control condition with set D1 excludes week 1. To use subset D1 directly as the controlling index set is a good idea. We start off by stating that the storage level now must be equal to the storage level of previous week. With dollar control avail, we include the storage variable only if the storage is available. Next, we will check the correctness. From the equation listing, we can see one constraint for each storage from week 2 to 4. We can also see that the shipping to and from the storage is not yet considered in the constraint. Next, we add items that are shipped from another storage. We sum over all the shipments from previous week. Note that the indices S and W are driven by the indexed equation. Furthermore, in the summation we refer to the previous week W-1. Moreover, S and W is controlled by the constraint and can be considered fixed within the summation. On the other hand, S' is not controlled by the indexed equation. Hence, this means that all shippings from other storages S' to the storage S is summed up. Similarly, we can subtract all the shippings that are shipped to another storage from the previous week. However, Now we change the order of sets S' and S. Next, we will check the correctness. We can look in the equation listing at week 2 for storage 1. We can see that all items from storage 1, week 1 needs to be shipped to storage 2 or 3. We can look at week 2, storage 2, and consider this as the current storage. We can see that shipping from storage 1 and 3 are added to the current storage. We can also see that storage items from the earlier week are added to the current storage. Furthermore, we deduct the shipping at week 1 that are shipped from storage 2 to storage 3. Another way to check for correctness is to look at the column listing. Here we see in which equation a variable appears. Variable ship week 1 from storage 1 to 2 appears in constraint E3 twice. First at week 2 storage 1 and another time at week 2 storage 2. Hence, in the first case the variable takes away items from storage 1, and in the second case the variable adds items to storage 2. We can see that this pattern holds for all instances of variable ship. Next, we will add the storage capacity restriction. We could add a constraint that restricts the number of items a storage can store each week. However, it is better to specify an upper bound to the storage variable. We specify the upper bound by using the variable attribute up. We assign the storage capacity as upper bound. This will have the same effect, but now the resulting model will have less constraints. A model where variable bounds are used instead of constraints is generally preferred by the solvers. We run the model and check the result. The total cost is $1,495, which seems to be reasonable. We can also see that the storage level and how the items are shipped from the one storage to another. You can find this example model and many more from the model libraries. If you want to read more about indexed equation, then you can, for example, open the Macau guide. You can search in the Macau guide for unnecessary equations, which will find the chapter Avoiding Considering Unnecessary Cases.